For my calculus project, I will be measuring and comparing the braking distances of two different cars, using everyone's favorite topic from calculus, Riemann sums. I started by finding a suitable location, which needed to be mostly flat, as straight as possible, and have very few cars driving on it. After a bit of searching, we came across this stretch of road outside of Novato on the backroads that looked pretty much perfect for our testing. The way Riemann sums works is you take different velocities, in our case miles per hour of the cars, and the time at which the speed occurred to get the overall distance an object traveled. There are 4 methods of Riemann sums we used: left, right, midpoint, and trapezoidal. Our setup consisted of 3 cameras, one watching the speedometer in slow motion for the most accurate data collection, one facing forward out of the car, and one at the braking zone filming an outside view. As a reference, we made a line of where to hit the brakes on each run, and then measured the distance using a long measuring tape to get the real-life distances each car traveled. Then we can use Riemann sums to see how accurate each method is. Let's start by looking at car 1's run. Using the slow motion video of the speedometer at the time interval of 15 frames, which is equal to half a second, I was able to make this table of data. The real-life distance recorded was just under 112 feet from 60 to 0, which is pretty good, but let's see what the different methods of Riemann sums tells us. Looking at the results, we see that each method was many feet higher than the measured distance, which makes sense because we didn't account for the time it takes to press the brake pedal and, much more importantly, how delayed the speedometer is. Even after I could see the car come to a complete stop, the miles per hour still read 7, and the speedometer only updates every quarter second, losing some valuable data from right when I first slammed on the brakes. Now let's look at car 2. This car's speedometer updates its speed much faster than car 1, so we can use a smaller time interval of 5 frames, which is about 1/6 of a second, which made this dataset. The real-life braking distance recorded was an amazing 104 feet, but let's see what the Riemann sums tells us. Same story as the previous test, each method was higher than the real-life distance. This time though, the data was much more accurate due to the much faster updating speedometer. Based on the data found in this very obscure, strange use of Riemann sums, the right Riemann sum was the best method used and got closer to the real distance recorded. If the data collection was much more accurate, trapezoidal may have been the best because it would have fit the shape of the deceleration graphs much better than any other method.